Hi, everybody. Here I am at Hogwarts, and we're going on to 1.5 now. And what is it about calculus that separates it from, let's say, like algebra or geometry, or like that? And the thing that really distinguishes calculus from all those other things is a concept called limits. And I want to explain a little bit what that means. So let me share my screen with you first. Okay. And oops, I don't want that. But it's an hour to I need this thing to, okay, there we go. We don't need that. Anyway, this is what we're doing is 1.5. Oh, I hate well, now we're waiting for an hour. It's so annoying. Anyway, 1.5 limits, that's what we're doing. And suppose I would ask you, what is the value of x squared minus 1 over x minus 1 if x equals 1? Now, I know what you're going to say. You're all going to say, well, it's undefined. Because if I plug in x equals 1, I get a 0 on the bottom of a fraction. And this is what calc is about. Calc is about something called limits, meaning that for when x equals 1, to know the value, well, it's impossible because, x can't equal 1 because if I put 1 in, it becomes undefined. So calculus says, all right, fine, it's impossible, but let's do it anyway. In other words, we never actually put in 1, but let's see what happens when we put in numbers that get very close to 1. That's what calculated. That's what limit is. So we say we want to look at the limit as x goes to 1 of x squared minus 1 over x minus 1. And I did that a little bit here. So here's this column is x. This column here is x squared minus 1 over x minus 1. And if you notice 0.9, 0.99, when x gets very close to 1, this expression really gets very close to 2. See, from this direction, it's getting 2.1, 2.01, 2.0001. Here's 1.9, 1.99, 1.99. So you can see from both sides, it's getting very, very close to 2. So I would say that the limit, is, oops. The limit is 2. Well, the limit of this, function as x approaches 1 is 2. The limit as x approaches 1 is 2. And that's limits. And that's really what makes calculus different than anything else than algebra, because we may not ever know, we can't plug in x equals 1, but too bad. So we're gonna figure it out anyway. Do you want to see what happens when x gets close to 1? That's what's happening. Alrighty. Let's do some math now. So how about the limit as x approaches 1 of x squared plus 1? Now, x squared plus 1 is really simpler because I don't have that problem of having x on the bottom of a fraction. The truth is that here I could just plug in 1, and I get 1 squared plus 1, which is 1 plus 1, which is 2. I could always just do that. But I could also do what I did before, making a table out of it. And as you see, as I get closer and closer, as x gets closer to 1, in fact, here, x could actually equal 1, but it is 2. So here it's getting 1.8, 1.98, 1.998. From this direction, it's 2.2, 2.02, 2.002, and so on and so forth. And that's the idea of a limit. So we want to find the limit as x approaches 1 of these various functions. So here's x squared minus 1 over x minus 1. This is an example I actually gave you when we started the class. Now, if you graph this, by the way, the graph is really interesting. It winds up looking like a straight line with a hole in the middle, because that hole is when x equals 1. When x equals 1, it's undefined. But even though it's undefined when x equals 1, we see that as x gets close to 1, the y value gets close to 2. And that's what limits are. The limits are, we don't care what happens when we get to the point in question. We want to know what happens as we get close to that point. All right, here is absolute value of x minus 1 over x minus 1. And again, the graph is going to look like this. And now it has a question mark here. Why is that? Because when x approaches 1 from the from the bottom, you know, 0.9, 0.99, 0.999, then f of x approaches -1. In fact, it actually equals -1 the whole way through. But when x comes from the other direction, 1.1, 1.01, 1.0, then the y value is 1 the whole way through. Well, what's the limit? If it's approaching -1, if it's getting very close to -1 on this side, very close to, there is no limit because it's a question mark. Because I can't. Now I could say there's what they call a right-hand limit of 1, because when I come from the right side, it's 1, and a left-hand limit of -1, but there's no overall limit. And let's see which that was. And C, this is the graph for C. We didn't just say what that function was. C was f of x equals x if x does not equal 1, and if x equals 0 if x does equal 1. So if x does not equal 1, when x does not equal 1, it's just y equals x. When x equals 1, then y equals 0. So it's basically like a straight line. There's a hole in the middle, but the value of that hole gets knocked down here. And again, but the limit is still going to be, 1, because if you notice, the y values from both directions are getting closer and closer to 1. They're coming from opposite sides, but they're getting closer and closer to 1. So the limit, so in this case, the limit is 1. In the so just to review, the limit was 2. In this one, the limit was undefined. There was no limit, and here the limit was 1 for C. Okay, let's move on. Okay, let's see. So we read it like this: the limit as x approaches C is some number, it's x value. The limit as x approaches C of f of x equals L. So L is some number, whatever the y value would get. Not that the y value necessarily equals, but the y value gets very close to that. And as x approaches C. So a function can have a limit. You have a limit even if it doesn't have a value. Many times the limit. Now sometimes I can just plug in C. I can just plug the number in, no problem. Now let's look at some basic limits. If B and C are real numbers, and n is a positive integer, then the limit as x approaches C of B is just equal to B. It's just equal to itself. That does not make any sense. I think it's a typo. Let me just think about this for a second. Let's look at the typo. Yeah, I take it back. It's not a typo. X approaches C of B. Now, B is just a number. It's a constant. It doesn't change. So it doesn't matter. X can approach whatever it wants. B is always just B. Now, the limit as x approaches C of x is equal to C. So the limit as x approaches 3 of x, I just plug in x equals 3, and the answer is 3. The limit as x approaches C of x to the nth power is C to the nth power, because I just plug in C for x. C is some constant. And the limit as x approaches C of the nth root of x is just the nth root of C, because I'm just plugging in C. So let's look at some examples of that. The limit as x approaches 2 of 3 is just 3, because 3 never changes. That's why it's called a constant, never changes. So 3 is equal to 3, and it doesn't matter what x is approaching. The value of the function is always going to be 3. The limit as x approaches -4 of x. Well, if x approaches -4, in this case, I can just take the -4, stick it into the x, and I just get -4. Here I take 9, stick it into the x, and I just get square root of 9, which is 3. Here I take 2, stick it into the x, I get 2 to the third, which is 8. So sometimes you can just take the number, the limit number, and you can just plug it in. Sometimes you cannot just plug it in because it might be a case of being undefined or so forth like that. But there are certain simple cases where you can just plug it in. Here are some properties of limits. Here are some properties of limits. Now, when you find the limit of a polynomial function, So polynomials, you could just plug in the 2 into the polynomial. X is approaching 2, so this becomes 2 squared plus 2 times 2 minus 3. So 2 squared plus 2 times 2 minus 3. Alrighty, and that is, and if I would say the x down here, as x approaches 1, that will be 2 minus 1 plus 4, which is 5. So if you have a polynomial function, just stick the number of c, whatever that number is, the limit number, and stick it into the polynomial, and that's going to be your answer. Like we stuck in 2, we stuck in 1, so on and so forth. Okay, now let's look at some techniques that'll make it easier, because here's the case. See, if I would just plug in x equals 1, the top becomes 0 and the bottom becomes 0, and that's undefined. The 0 on the bottom is undefined. But sometimes I can do something cool. I can cancel stuff. In other words, x to the third minus 1 is equal to x minus 1 times x squared plus x plus 1. You probably learned that in algebra at some point. It's called the difference of two cubes. And I'm dividing that by x minus 1. Well, I have the x minus 1 factor on top and the x minus 1 on the bottom. They just cancel out. I'm left with x squared plus x plus 1. And now I can just plug in. See, before I couldn't just plug in x equals 1. I would get 0 over 0. But now I can just plug in x equals 1. And I get 1 plus 1 plus 1, which is 3. So the answer is the limit of this is 3. 3. Very remarkable. This actually, we could have done this, so we're going to get to that. X cubed minus 1 over x minus 1 actually looks like this. It's like a parabola with 1 point missing. And in fact, this is the parabola. This is the parabola with the point But when I have this, x cubed minus 3 over x minus 1 is the same as this parabola x squared plus x plus 1, except it's missing that 1 point. So that's pretty cool and awesome. I just want to go back here. So we had that case right there. So what I could do here is that I could factor x squared minus 1 with the x cubed. See, this is equal to x plus 1 times x minus 1, and that's divided by x minus 1. So just 1's equal to x plus 1. And we were talking, so now if I plug in 1, I get the limit now is just 1 plus 1. So 1 plus 1 equals 2. Because now now that there's no more problem of having a 0 on the bottom of a fraction, I can just, after making this cancellation. Now, I can't actually do it, but how do I say this? It's still undefined, but at least this tells me what the limit would be. That's the best way I can say it. Okay. How about this one here? Well, the top is a quadratic which can be factored. Not all quadratics can be factored, but x squared plus x minus 6 becomes x minus 2 times x plus 3, and the x plus 3 on top cancels the x plus 3 on the bottom, and I'm left with x minus 2. Now I just plug in x equals -3, and I get -5. So the limit is -5, and again, it's going to be a function which has a hole at -3, -5, but at least that's where the hole is. It's very holy. Okay. Square root of x plus 1 minus 1 over x. Now again, if x equals 0, if I would just plug in x equals 0, I get 0 on the top, 0 on the bottom. I can't have 0 on the bottom, so I'm going to have to do something tricky. Now I'm going to have to be a little tricky here and do some little slick algebra moves here. Square root of x plus 1 minus 1 over x. I'm going to multiply it by rad x plus 1 plus 1 over rad x plus 1 plus 1. I have to multiply it by 1. But when I multiply this guy by that guy, this is like a plus b and a minus b. So it becomes a squared minus b squared. Well, the radical squared, just the radical disappears. So you get x plus 1 minus 1 over x times rad x plus 1 plus 1, because I'm just multiplying that all out. But now x plus 1 minus 1, the plus and minus 1 cancel, so I just have plain x. And now that plain x cancels with the x that's down on the bottom. I'm left with 1 over rad x plus 1 plus 1. Now I'm going to have no problem plugging in x equals 0 on the bottom. Because if I plug in x equals 0 on the bottom, I just get 1 over radical 0 plus 1 plus 1, which is 1 over 1 plus 1. We know 1 plus 1 equals 2. We already learned that in the last problem, and becomes 1 over 2, 1/2. And that's the limit of this function. And there's no way you would just look at it and guess that. But we had to do it by this slick algebraic cancellation. Now I mentioned for a one-sided limit, because we saw a function before where on one side, see here, on the right side, the limit is just 2, because the x value is always 2 as I get close. As x gets close to 0, the x value is always 2. And here, when x gets close to 0, the x value is always -2. So we can talk about a right-sided limit, or they call it a positive limit. So you see it says x goes to 0 plus. So it doesn't mean positive 0. There's no such thing as positive 0. It means when x goes 0 from the positive side, the limit is 2. When x approaches 0 from the negative side, see a little minus there, the limit is -2. So that's not positive 0, -0. That means coming from the positive side versus coming from the negative side. And if the two sides are the same, if the left side and the right side are the same, then we say there's an overall limit. But you can have you can have a positive, right-sided limit and a positive. You can have two good limits from each side, and which do not agree with each other, and that's fine. See, so if the two limits are different, then there's a left hand and a right hand. If the two limits are the same, then there's an overall limit. Okay, let's look at this function here as x approaches 1. So 4 minus x over 4x minus x squared. Well, now if you notice, there's no problem here of the function being undefined when x equals 1, except that we never have x equals 1. And like 1 is not part of the domain. We're talking about the function is only defined for numbers less than 1 and numbers more than 1, but it's never defined for 1 itself. So 4 minus x, if you graph it, looks like that. And 4x minus x squared is like this sort of upside down parabola. And there's a hole there, not because I'm dividing by 0, but just because this function, the way in the definition of the function, there was never any allowance made for x equals 1. So that's just it's just the way it is. So the limit, nonetheless, the limit here is 3, because whether I come from the right side or whether I come from the left side, the y values are getting closer and closer to 3 as the x values get closer and closer to 1. And that's the way this guy works. unbounded means it gets like infinitely big. So the limit is x goes to 2 of 3 over x minus 2. Well, the bottom is if I plug into the bottom, always start by seeing what happens if you plug the number in. If I plug into it, I get 0 on the bottom and 3 on the top. Now, if I would graph this, you get this guy right here, which is a hyperbola. When x approaches 2 from the positive side, it goes up to positive infinity. When x approaches 2 from the negative side, it goes down to negative infinity. So there's a right-sided limit of positive infinity. There's a left-sided limit of negative infinity, but there's no overall limit because the right and the left don't agree. And there you go. Okay, I'm going to give you guys some fabulous homework to do because I know you can love good homework. So I'm going to put the homework in Canvas like I always do, and that will be the story with that. So let's get some nice good homework problems. Okay, let's see. I want to do now before I'm going to assign some homework. But let's look at some of let's look at some of the even problems. I'm going to assign odd problems. Let's look at a few of the even ones. Give you the idea. So we want the limit as x approaches 1. Well, when x approaches 1, here's 1, but y just approaches -2. There's no problem there. When x approaches 3, then y just approaches y is equal to 0. So the limit as x approaches 1 is just -2. The limit as x approaches 3 is just 0. And this is a simple one. I can just plug in the numbers in, no problem. Notice that they never told us what the function was. It just drew us a picture, and that's fine. Well, these guys here, you're just going to plug in, crunch out different values of the calculator. Limit as x approaches 10 of x, just equal to 10, because you just take 10, plug it into the x, and the answer is 10. So that's a very simple one. The limit as x approaches -1 of the cube root of x. Well, again, it's not undefined. I could take -1, plug it into the x. Cube root of -1 is -1. Now you're all thinking to yourselves, hey, you can't put a negative number into a radical. Well, you can't put a negative number into a square root, but you can't put it into a cube root. If the root is odd, you can put a negative number in. If the root is even, you cannot put a negative number. Oh, let's see what else it is. Now this one, I have a fraction, but if I put in x equals -2, it's not a problem because I get 2 minus -2, which is +4. So I have 3 times, on top I have 3 times -2, which is -6, plus 1 is -5. So it's just -5 over +4, and that's it. Again, you just plugged it right in because there's no problem. Now, yeah. For something like number 40, I'm going to factor the top and the bottom, and there's going to be a t minus 1 that's going to cancel out. And then you just plug, then whatever's left. I like number 40. Let's do that on the. So this reduces, I can factor this. the top is t minus 1 times, why is it? The top is t minus 1 times t plus 2. The bottom is t minus 1 times t plus 1. And that winds up canceling, and you wind up getting, actually, we highlighted cancel. So canceling the t minus 1. The ones are getting canceled, and I get t plus 2 over t plus 1. And then when I plug in t equals 1, I just get 1 plus 2 over 1 plus 1. And that, of course, that just equals 3 over 2. I guess technically I should put a little parentheses. And we are, there you go. Well, it's been loads of fun, and we'll see you guys next time. Bye, everybody. Bye.